The universe begins, or at least that is how the story is usually told. In the language of cosmology, it starts as a single event, a beginning compressed into an instant that cannot be replayed or visited, only inferred from the faint traces it leaves behind. Space stretches, time starts to flow, and energy pours into existence in forms that later harden into particles, atoms, stars, and worlds. Beneath this confident outline, a quieter uncertainty moves like a current under still water. The equations that describe the very early universe agree with observations, but only from a tiny fraction of a second after the supposed beginning. Before that fraction, the line of calculation enters a fog. At the edge of that fog waits a question that refuses to disappear. What does it mean to say that time itself begins? Telescopes and detectors stand scattered across deserts, mountains, and orbits, listening to the leftover light of that violent dawn. They measure a cosmic background that bathes all of space in an almost perfect glow, a faint microwave afterimage cooled by almost 14 billion years of expansion. Its temperature varies only by tiny amounts from place to place, a pattern of gentle modeling that records the first ripples of matter and energy. From these ripples, cosmologists reconstruct the early universe as a hot, dense plasma, a sea of charged particles and light so tightly bound together that no clear beam can travel far without being scattered. In this picture, the young cosmos resembles the inside of a star, but everywhere, in every direction, an ocean of brightness that no eye can see through. For all its heat and violence, this early plasma follows rules that are well understood. The physics of particles, radiation, and gravity combine to explain how the glow cools, how atoms appear, how the universe becomes transparent, and how the first clumps of matter slowly gather under their own weight. Satellite maps of the background light show a pattern that matches these calculations with striking precision. The story from the first minute onward rests on firm ground. Stars and galaxies arrive on schedule, elements form in the predicted proportions, and the large-scale structure of the cosmos, a vast network of filaments and voids, grows from the faint seeds written in that early modeling. Yet when those same equations are pushed backward, they do not soften into a graceful origin. Instead, they curve inward toward an impossible point of infinite density and zero volume, a mathematical singularity where every familiar quantity diverges. Safely away from that point, time behaves like a smooth dimension that can be followed in either direction. Close to it, time becomes suspect. Durations shrink, intervals blur, and the notion of a before becomes tangled with the very geometry being described. The singularity is not a place that can be reached even in imagination. It is a warning that the theory that works so well elsewhere has entered a domain for which it is not built. The early universe invites comparison to a film played in reverse. Galaxies draw together, clusters tighten, gas heats, and radiation grows intense as the frame count moves back. Extrapolation compresses all of this into a single frame, then a single point, and then into something that no longer deserves the name point at all. At that stage, the mathematics stops describing a world and starts describing its own limitations. Relativity treats space and time as a continuous fabric. Quantum theory insists that at very small scales, energy and fields must fluctuate. Where both effects matter strongly, the smooth fabric begins to look more like foam, restless and uncertain, and the ordinary meaning of location and duration no longer applies. Observatories cannot see into this domain. They record light and particles that leave their sources long after the first instant has passed. The youngest image available to any instrument is the frozen pattern of the background radiation produced when the universe is already hundreds of thousands of years old. Behind that image lies an opaque wall of plasma that no beam of ordinary light can cross. The story earlier than that must be pieced together from indirect clues: the composition of the elements, the arrangement of galaxies, and the possible whisper of primordial gravitational waves that present detectors only hope to sense. These clues point consistently toward an origin in a hot, dense state. They say nothing clear about whether that state arises from nothing from a previous phase or from something that does not resemble time at all. The idea that time begins with the expansion confronts the mind with a paradox hidden in ordinary language. To speak of before is to assume that time already exists, that there is a container in which earlier and later can be arranged. If time itself is part of what emerges, then asking what happens before it may be similar to asking what lies north of the North Pole. The direction exists only within a certain geometry. Beyond that geometry, the word loses its meaning, even if it still feels natural to ask the question. As measurements sharpen and simulations grow more detailed, the boundary close to the beginning becomes both clearer and more mysterious, a narrow region where the standard description of an expanding universe still points back to a place that current theories cannot reach, and where the question of what it means for time to begin continues to wait in the dark. In the earliest fraction of a second after the expansion begins, the universe passes through a phase that current theory calls inflation, a word chosen to suggest an almost unimaginable stretching. A region smaller than an atom swells to cosmic size in an instant so brief that ordinary language cannot easily contain it. The physical mechanism behind this inflation is still uncertain, described in terms of a field that fills all of space and a form of energy that resists collapse, but the fingerprints of this event appear again and again in the sky. The most striking trace lies in the almost perfect smoothness of the leftover microwave glow. Viewed across the entire heavens, this ancient light has nearly the same temperature in every direction. Only tiny variations break its uniformity, faint mottled patches that mark places where the early plasma was slightly denser or thinner. The smoothness is itself a puzzle. For distant regions of the observable universe to share the same temperature, they must once have been close enough to exchange light and heat. Under a simple expansion without inflation, those regions would never have been in contact. They would always have been separated by more distance than even light could cross in the time available. Inflation solves this horizon problem by placing every point of the visible universe inside a single tiny patch before the great stretching. In that early closeness, heat spreads and temperatures even out. When inflation drives that patch outward at tremendous speed, the uniformity is spread across a vast domain. The explanation is elegant, but it depends on a form of energy that has never been observed directly and on a field that switches behavior in a finely tuned way. As satellites refine their maps of the ancient glow, they find patterns that fit the predictions of inflation with impressive accuracy, but they also hint at small tensions. Certain large-scale variations appear slightly stronger than expected. A subtle alignment in the hottest and coldest spots stretches across the sky in a way that no simple model predicts. Some researchers treat these features as statistical accidents, the natural flukes that occur when random fluctuations are painted on a single observable sky. Others wonder whether they might be faint messages from physics that lies beyond the standard picture. If inflation happened, it may not have been a single smooth event, but a more complicated sequence of surges, pauses, and transitions. In some versions of the theory, inflation does not end everywhere at once. Instead, it continues in distant regions, creating an ever-growing mosaic of space where the expansion never fully stops. Our observable universe becomes one bubble among many, a local calm in a larger multiverse that forever blossoms. In that scenario, the properties of matter, the strengths of forces, even the number of spatial dimensions could vary from bubble to bubble. The cosmos that telescopes can see would then be a small and ordinary patch of a far larger and stranger construction. No direct observation presently confirms such a picture, yet it hangs at the edge of the discussion whenever inflation is mentioned, a reminder that the simplest way to solve the early puzzles may come with expansive consequences. Below the level of grand speculation, inflation leaves more concrete traces. It amplifies quantum fluctuations, the tiny jitter in fields and energy that cannot truly be set to zero. During the ultra-rapid stretching, these microscopic ripples are pulled to astronomical scales. Once frozen into the plasma, they become the seeds of future structure, the places where matter will slowly gather into filaments, clusters, and galaxies. Measurements of the microwave patterns reveal exactly this kind of spectrum, with small fluctuations more common and large ones rarer in a proportion that matches the idea of magnified quantum noise. Here, the story of the universe merges the deepest small-scale physics with the broadest cosmic architecture. Randomness at the smallest scales is written into the largest patterns of sky. Yet the translation is not entirely transparent. Quantum theory describes probabilities, not single histories. The early universe must in some sense embody every possible distribution of fluctuations, then settle into one realized pattern, the particular modeling that satellites actually record. The question of how this transition from many possibilities to one outcome occurs is part of a wider puzzle about measurement and reality in quantum mechanics. In ordinary experiments, the act of observation involves instruments and observers that are clearly distinct from the system measured. In the early universe, there is nothing outside the system. Whatever process selects one pattern from many must happen without any external observer at all. Various approaches attempt to tame this problem from interpretations that treat all outcomes as equally real in a branching multiverse to ideas in which decoherence, the spreading of quantum correlations into many degrees of freedom, makes certain patterns effectively classical. None of these stories commands universal agreement, and all operate near the edge where language built for everyday experience begins to strain. Inflation, therefore, sits at a crossroads. It explains many features of the observed universe and links the birth of structure to the restless vacuum of quantum theory, but it also opens questions about the larger reality in which the observable cosmos might be embedded, and about the way randomness and possibility become the specific web of galaxies that actually exists. As a model, it brings the beginning into sharper focus, while at the same time surrounding that beginning with new layers of mystery. In the first few 100,000 years of its history, the universe changes character in ways both simple and profound. What begins as a blinding plasma of particles and radiation slowly becomes a clearer, more structured place, though no eye yet exists to see it, and no solid surface yet forms to mark the change. The cosmos expands, and as it expands, it cools. Temperatures fall from unimaginable values to levels where new forms of matter can survive. Protons and neutrons forged in the first minutes drift through a sea of light and electrons. Collisions are constant, but gradually the fury becomes less intense. The rate of interaction slows as space grows larger and particles are spread farther apart. In this era, light does not travel freely. Every photon, every particle of radiation scatters again and again off charged particles, especially electrons. The universe is bright but opaque, like the interior of a star extended to cosmic size. Although the details are turbulent, the overall pattern remains simple. Gravity pulls matter together, pressure pushes it apart, and radiation streams through the mix, always being deflected, never finding a clear path. Tiny variations in density that inflation has left behind begin to matter. In regions that are slightly denser than average, gravity has a little more to work with. In slightly emptier regions, expansion wins more easily. The universe becomes a subtle contest between clumping and dispersal written in small differences. The composition at this time is strikingly plain. Almost all atoms exist as simple hydrogen, a single proton paired with a single electron, or as helium built from a small cluster of protons and neutrons. A trace of lithium appears, but nothing heavier. There are no carbon chains, no complex molecules, no dust grains. The familiar ingredients of rocks, oceans, and living cells do not yet exist. The young cosmos is simple in its chemistry, but already complex in its motions. Over time, cooling continues. When the temperature falls to a few thousand degrees, a quiet transformation takes place. Electrons that once wandered freely begin to bind to protons, forming neutral atoms. With fewer free charges to scatter them, photons can finally travel long distances. The fog thins in a sudden and dramatic way, even though the change unfolds over thousands of years. The universe becomes transparent. This moment of decoupling between matter and radiation leaves a permanent record. The light that escapes then continues to stream through space, gradually stretched to longer wavelengths by the ongoing expansion. What once was a flood of visible and infrared light shifts into the microwave band, cooled by the growing size of the cosmos, until its temperature settles just a few degrees above absolute zero. This relic glow, called the cosmic microwave background, fills every direction. It is the oldest light that can be observed, the earliest photograph the universe leaves of itself. When instruments map this radiation, they see an almost uniform field speckled with small irregularities that reflect the density ripples present at the time of decoupling. Each slightly warmer patch marks a region that was denser and under stronger gravity. Each slightly cooler patch marks a more rarefied place. From this delicate pattern, cosmologists reconstruct the conditions of the universe at an age of roughly a few 100,000 years. The agreement between theory and measurement in this domain is remarkable. Simple models that assume a universe filled mostly with dark matter and dark energy, plus a smaller portion of ordinary matter and radiation, reproduce the observed spectrum of fluctuations with high precision. The heights and positions of the peaks in that spectrum depend on how fast the universe expands, how much matter it contains, and how much of that matter interacts with light. By adjusting these parameters, researchers fit the data and recover a consistent picture in which the cosmos is spatially almost flat and has a specific age and composition. Yet even in this apparent triumph, subtle tensions appear. Measurements of the expansion rate inferred from the background light do not quite match those obtained from distances to nearby galaxies and exploding stars. The discrepancy is small in absolute terms but persistent, and it may hint that the simple model misses some aspect of the true story. Perhaps the dark energy that drives the current acceleration of the universe changes over time, or perhaps unknown particles contribute to the early expansion in ways not yet fully appreciated. The cosmic microwave background thus serves both as a confirmation of the broad outlines of the standard model and as a possible doorway to new physics. It Beyond its role as a tool for measurement, this ancient light has a more intimate significance. It marks the first moment when the universe becomes visible in any meaningful sense, the first time that a photon can cross great distances without being trapped by the plasma. Long before stars ignite, long before galaxies assemble, the cosmos already shines with this soft, uniform glow. The fact that modern instruments can still catch this radiation is a reminder that the universe remembers its own childhood with extraordinary fidelity. Every patch of sky, no matter how empty it seems to the unaided eye, holds within it a faint echo of that transition from fog to clarity. Within that echo lies the imprint of the tiny fluctuations that will one day grow into clusters, superclusters, and vast cosmic voids. The seeds of every future star and planet are written as slight temperature differences on this ancient backdrop, a quiet design that guides the later, more dramatic phases of cosmic evolution without revealing yet how the story truly began. In the long interval after the universe becomes transparent, but before the first stars ignite, space enters a phase later called the Cosmic Dark Ages. The name describes not only the absence of starlight, but also the present difficulty of observing this era directly. The hot plasma has cooled into a calm gas of neutral hydrogen and helium. The background glow of ancient radiation still fills all of space, but it has faded into a uniform microwave whisper, too cold and too smooth to reveal what the gas is doing on smaller scales. Gravity, however, continues its patient work. Tiny density fluctuations frozen into the matter at the moment of decoupling begin to grow. In regions that start slightly denser than the cosmic average, gravity pulls matter inward a little more strongly, and that extra pull attracts still more material. Over millions of years, small advantages accumulate. Filaments form as gas and dark matter stream along invisible gradients. Where several filaments meet knots of higher density, emerge the seeds of future halos in which stars and galaxies will eventually gather. During the Dark Ages, these structures remain invisible in ordinary light. The gas that falls into them heats as it compresses, but not enough to glow with brilliance. Neutral hydrogen interacts weakly with the background radiation, slightly absorbing or emitting at a characteristic radio wavelength that future instruments hope to detect. In principle, a full map of this signal would reveal the growth of structure through the entire dark era, but in practice the measurement is extremely difficult, and for now the scene must be reconstructed mainly from theory. In the densest knots of gas cooling processes eventually allow matter to lose enough energy to collapse further. Small clumps form then larger ones as molecular hydrogen permits gas to shed heat and contract. When the central regions of these clumps reach high enough density and temperature, nuclear fusion begins. The first stars are born. These primordial stars are not like the familiar stars that later fill the spiral arms of galaxies. With no heavy elements to help the gas cool and break apart, the first stellar embryos grow massive, perhaps dozens or hundreds of times the mass of the present sun. Their lives are brief on cosmic scales, burning through their fuel in only a few million years. Their light, once it escapes the dense birth clouds, transforms the surrounding darkness. Intense ultraviolet radiation pours outward, stripping electrons from nearby atoms and carving expanding bubbles of ionized gas into the neutral medium. As more stars form in more halos, these bubbles grow and begin to overlap. The universe enters a new transition known as reionization. Slowly, over hundreds of millions of years, much of the intergalactic hydrogen becomes ionized again, not by a uniform heat bath, as in the early plasma, but by the combined glow of countless young stars, and by matter falling into the first black holes. The details of ionization are still uncertain. Different models predict different timelines and different mixtures of sources. Observations from large ground-based telescopes and from space-based observatories glimpse galaxies that shine when the universe is only a few 100 million years old. Some appear surprisingly bright and compact, suggesting that star formation and the assembly of structure progressed faster in some regions than simple theories anticipated. These findings raise questions about the behavior of dark matter, the efficiency of gas cooling in early halos, and the possible presence of processes that boost the rate at which stars assemble. As the first generations of stars live and die, they alter the chemistry of the cosmos. Within their cores, hydrogen fuses into helium and helium into heavier elements such as carbon, oxygen, and nitrogen. In their violent deaths as supernovae, the most massive stars scatter these elements into the surrounding gas. The pristine simplicity of the early universe gives way to complexity. New clouds enriched by stellar debris can cool more efficiently, fragment into smaller pieces, and form more modest stars, some of which may survive for billions of years. Around these longer-lived stars, disks of gas and dust can condense into planets. Thus the era that begins in apparent emptiness and darkness becomes the forge of every subsequent structure, including the raw material for life. The cosmic dark ages are therefore dark only in a visual sense. Dynamically and chemically, they are a time of intense preparation when gravity quietly builds the scaffolding on which all later history will rest. Yet this entire chapter of the story remains only partially seen. The light from the first stars is stretched by expansion into faint infrared wavelengths by the time it reaches present instruments. Space-based observatories such as the James Webb Space Telescope have revealed galaxies so distant that their light has traveled for more than 13 billion years, pressing observational knowledge deep into the era of reionization. Still, the true first star, the earliest object to ignite fusion in a previously dark cosmos, remains beyond detection and perhaps always will. Its existence is inferred rather than witnessed, a necessary but unseen bridge between the smooth film of the microwave background and the crowded tapestry of modern galaxies. At this boundary between darkness and light, the universe demonstrates a pattern that repeats throughout its history, periods of quiet accumulation leading to sudden change, with the dark ages gathering matter into invisible structures until a threshold is reached and the first stars burst into being, ending one kind of night and beginning another under the glow of newborn suns. As the first waves of massive stars flare and fade, the universe enters a new phase in which light and structure begin to trace out a cosmic pattern that will persist for billions of years. The small knots of dark matter and gas that formed during the Dark Ages grow by attracting their neighbors, merging into larger halos whose gravity can hold vast reservoirs of material. Within these halos, cold gas sinks toward the center, cooling through radiation and fragmenting into countless clouds. Each cloud becomes a cradle for new generations of stars less massive than their primordial predecessors, but far more numerous, forming loosely bound associations and dense clusters. Over time, these stellar gatherings assemble into the first recognizable galaxies. Some take on irregular shapes distorted by ongoing infall and collisions. Others settle into disks rotating gently around central bulges of older stars. Surrounding each galaxy, an extended halo of dark matter deepens the gravitational well, shaping the motions of the luminous material without ever revealing its own nature. The large-scale pattern of this growth is not random. Guided by the initial fluctuations imprinted in the early universe, matter flows along invisible ridges to form a web-like network of filaments and nodes. Simulations of structure formation run on supercomputers with billions of particles produce maps that closely resemble what telescopes later observe. Long strands of galaxies threading empty voids, clusters forming where filaments intersect, and superclusters weaving together into a scaffold that spans hundreds of millions of light years. In this picture, dark matter provides most of the mass and dictates the framework, while ordinary matter paints the visible details, condensing where the dark skeleton is thickest. The agreement between simulation and observation gives strong support to the idea that an unseen component dominates cosmic structure, yet it also draws attention to subtler discrepancies. On the scales of galaxy clusters and above, the model works with impressive precision. Gravitational lensing, the bending of light from distant sources, by intervening mass reveals patterns that match the distribution of dark and luminous matter predicted by theory. But on smaller scales within individual galaxies and their immediate surroundings, tensions appear. The simplest dark matter models predict that halos should have sharply rising densities toward their centers, forming what are called cusps. Observations of dwarf galaxies and low surface brightness galaxies, however, often suggest flatter central profiles more like cores than cusps. In addition, numerical simulations produce great numbers of small dark matter subhalos around larger galaxies, far more than the number of visible satellite galaxies actually observed around systems like the Milky Way. Astronomers refer to this mismatch as the missing satellites problem. Some of these small halos may remain invisible because they never acquire enough gas to form stars, but the extent of the discrepancy leaves room for doubt. A related puzzle called the too big to fail problem concerns a subset of simulated subhalos that are massive enough that they should almost certainly form stars, yet there appear to be too few corresponding bright satellites in real data. These anomalies may be resolved through more detailed modeling of gas physics, star formation, and feedback processes that are complex and difficult to capture in simulations. Stellar winds, radiation pressure, and supernova explosions can push gas out of shallow potential wells, altering the distribution of matter and flattening central density cusps into cores. They can also quench star formation in smaller halos, rendering them dark. Improved numerical techniques and increasingly powerful computers are gradually incorporating these effects, and some studies show that the apparent conflicts lessen when baryonic physics is treated in more detail. Still, the tension between simple dark matter expectations and the diverse structures of small galaxies keeps open the possibility that something more fundamental might be at work. Alternative ideas propose that dark matter may not be completely cold and collisionless. If dark matter particles interact weakly with themselves or with other fields, they could redistribute energy within halos, smoothing out cusps and reducing the number of dense substructures. Other theories suggest that modifications to gravity on galactic scales could mimic the effects attributed to dark matter without requiring a new form of matter at all, although such models often struggle to reproduce the success of dark matter on larger scales. In this way, the formation of galaxies becomes not only a story of assembly, but also a laboratory for unknown physics. Each rotation curve, each satellite distribution, each gravitational lensing map provides a test of the invisible component that shapes the cosmos. Observations of colliding galaxy clusters add another layer to the mystery. In some famous systems, the luminous gas clouds that carry most of the ordinary matter are slowed and displaced by drag as they pass through each other, while the gravitational lensing signal peaks in regions offset from the gas, suggesting that most of the mass passes through without colliding. This behavior fits naturally with the idea of dark matter particles that rarely interact except through gravity, but even here the details can constrain how strongly they may scatter. If dark matter interacts too much, halos would be rounder and more mixed than observed. If it interacts too little, certain small-scale puzzles remain sharper. The universe thus presents a narrow window through which the properties of the unseen can be inferred. Amid this intricate balance, galaxies mature. Their central regions grow dense with stars, their outskirts remain faint and extended, and their halos stretch far beyond the visible disk. Supermassive black holes appear at their cores, somehow assembling millions or billions of solar masses in relatively short cosmic times. Jets and outflows from these central engines can heat and stir the surrounding gas, regulating star formation on large scales. The relationship between these black holes and their host galaxies, reflected in tight correlations between black hole mass and galactic bulge properties, hints at a deeper coordinated evolution whose mechanisms are still being unraveled. Through all of this, the original questions linger. Dark matter holds galaxies together, but its nature remains unknown. The cosmic web traces out a pattern seeded by quantum fluctuations and amplified by gravity, but the exact rules governing the unseen majority of the mass are not yet fully understood. Each successful match between simulation and observation strengthens confidence in the overall framework while turning attention toward the remaining discrepancies where new physics might hide. The galaxies that wheel across the night sky are therefore both finished structures and ongoing clues, their graceful arms and dense cores shaped by forces that invite recognition but still conceal behind their luminous stars an invisible architecture whose full character has yet to be revealed. Within the growing network of galaxies, time continues to pass on scales that dwarf any later measure of history. Stars form, shine, and die in uncounted numbers, each generation subtly changing the chemical character of the gas from which the next will be born. What begins as a universe made almost entirely of hydrogen and helium slowly acquires heavier elements forged in stellar cores and scattered by supernova explosions. Carbon and oxygen, silicon and iron, and many others drift outward in expanding shells, mix with cooler gas, and settle into new clouds. Over billions of years, this cycle of birth and death repeats, enriching the interstellar medium and making possible forms of matter that did not exist before. In these enriched clouds, the physics of cooling changes. Dust grains, tiny solids made from heavy elements, help gas radiate away heat more efficiently. Molecules form, some simple, some surprisingly complex, their bonds allowing them to emit energy at characteristic frequencies. As gas cools and contracts, it fragments into many smaller clumps than was common in the first generation of stars. The typical new star becomes less massive and longer lived. Disks of gas and dust surround these young stars, flattened by rotation and sculpted by turbulence and magnetic fields. Within such disks, the raw materials for planets collect. Tiny grains collide and stick, forming aggregates that grow from micron-sized motes into pebbles, then boulders, and eventually planetesimals that can pull in more matter with their own gravity. The details of this growth process are still an active field of study. Collisions can both build and destroy, and the balance between them depends on local densities, velocities, and the influence of gas. Some paths lead to rapid accumulation, others to fragmentation. Yet across many environments, the outcome is similar systems of planets, embryos, and debris arrange themselves around their central stars, locked into orbital patterns that can be stable for billions of years. In one ordinary spiral arm of one ordinary galaxy about halfway from the core to the outskirts, such a process unfolds in a cloud belonging to what will eventually be called the Orion arm of the Milky Way. A region of gas and dust collapses under gravity, perhaps nudged by the shock front of a nearby supernova or by the passage of a spiral density wave. Within this collapsing cloud, clumps form and condense into a small association of stars, each with its own circumstellar disk. One of these newborn stars, modest in mass and brightness compared with many of its siblings, stabilizes as a yellow-white main sequence star that will later be called the Sun. Around it, the leftover gas and dust in its disk begin to swirl and separate. Close to the star, where temperatures are high, volatile materials like water and carbon monoxide remain in vapor form, while metals and silicates condense into solid grains. Farther out, beyond a distance where temperatures drop below the condensation point of water ices can form, as well adding mass to the solid component. This region, often called the snow line, marks a boundary between inner rocky bodies and outer giants dominated by lighter elements. Within the inner disk, countless collisions among dust and rock gradually produce larger bodies. Some grow quickly, sweeping up their neighbors and carving gaps in the disk. Others are scattered into new orbits or ground back down into smaller fragments. The evolving swarm is chaotic, yet guided by the persistent pull of the central star and by the mutual gravity of its members. In the outer disk, beyond the snow line, solid cores can grow larger still by incorporating both rock and ice. Once a core reaches a sufficient mass, it can begin to accrete gas directly from the surrounding disk, forming envelopes of hydrogen and helium that dwarf the original solid seed. In this way, giant planets can assemble more rapidly than their terrestrial cousins, provided that the gaseous disk remains long enough for the process to complete. Observations of young stellar systems in the present universe suggest that protoplanetary disks generally persist for only a few million years before stellar winds and radiation disperse them. The timing of planet formation must therefore thread a narrow window between collapse and dissipation. The particular configuration that emerges around the Sun reflects this interplay of timescales and conditions. 4 small rocky planets occupy the inner orbits, separated by an asteroid belt of remnants that never fully coalesce. Farther out, 2 massive gas giants, followed by 2 intermediate ice giants, circle in paths whose near stability suggests a complex history of migration and gravitational exchange. Beyond them, a distant reservoir of icy bodies extends into the dark, forming a diffuse belt and perhaps a vast cloud that reaches toward interstellar space. The apparent order of this system, with nearly circular orbits and a clear division between inner rocky worlds and outer giants, long gave the impression of a natural template for planetary architecture. Yet as instruments capable of detecting planets around other stars began to survey the galaxy, a bewildering variety of arrangements emerged. Some stars host giant planets closer than Mercury, tidally locked and blisteringly hot. Others show systems of many super-Earths packed into orbits that would all fit within those of Venus. Eccentric orbits, inclined planes, and resonant chains reveal a history of migration and gravitational encounters far more dynamic than once imagined. Against this backdrop, the solar system appears both ordinary and unusual, sharing common features, yet lacking some of the extremes. The presence of Jupiter, with its enormous mass and relatively distant orbit, may have shaped the distribution of smaller bodies, influencing how much material reached the inner region and how many comets bombarded the young terrestrial planets. Numerical simulations suggest that slight changes in the early positions or masses of the giants could have produced very different outcomes, with more or fewer planets, different orbital spacings, or more frequent instability. The current arrangement, while stable on human timescales, rests on the memory of a more chaotic youth in which orbit-shifted bodies collided and debris was flung outward or inward. The degree to which such histories are typical remains unknown. The detection of exoplanets continues to expand the catalog of possibilities, hinting that nature explores a wide space of configurations. The formation of the solar system thus occupies a place in the broader cosmic story where the large-scale physics of gravity and gas dynamics narrows into individual details that may be sensitive to initial conditions and chance encounters. The same laws operate everywhere, but the outcomes diverge, producing systems that share a common origin in collapsing clouds, yet differ in architecture and potential. Within one such system on one small rocky world, under a modest star, future observers will one day look outward and reconstruct from scarce clues the long chain of events that led from the nearly featureless early universe, through the building of galaxies and stars, to the delicate arrangement of orbits and materials now circling quietly in the dark. Within the young solar system, the small rocky planet that will later be called Earth takes shape from the same swirling disk of dust and gas that surrounds the new sun. At first, it is one among many growing embryos, a cluster of planetesimals merging and colliding in a region only a few astronomical units wide. Gravity draws together fragments of rock and metal, their impacts releasing enough energy to melt large regions of the forming world. Over a span of tens of millions of years, this violent accretion builds a body with enough mass to hold an atmosphere and enough internal heat to remain geologically active. As the molten layers churn, heavier elements such as iron and nickel sink toward the center, forming a dense core, while lighter silicates rise to create a surrounding mantle and crust. This differentiation not only shapes the internal structure but also sets up the conditions for a magnetic field as the metallic core cools and slowly convects. The young Earth is far from tranquil. Its surface is a landscape of magma oceans, unstable crustal plates, and restless volcanoes that vent gases into a thickening sky. Into this chaos falls a final colossal impactor, a body roughly the size of the later planet Mars, arriving at a glancing angle. The collision melts much of the outer layers of both objects and ejects a vast plume of material into orbit. Over time, this debris coalesces into a single companion, the Moon locked in a gravitational dance with Earth and tugging on its oceans and crust for billions of years to come. The moon-forming impact strips away much of the original atmosphere and remelts the surface, resetting conditions near the top of the planet, even as the deep interior continues its slow evolution. In the aftermath, Earth cools again. Volcanic outgassing releases water vapor, carbon dioxide, nitrogen, and other gases. Comets and water-rich asteroids, left over from the outer regions of the disk, also contribute to the volatile inventory through repeated impacts. As the surface temperature falls below the boiling point of water, rain begins to fall upon the solidifying crust. At first it hisses into steam on hot rock, but gradually in lower regions and large basins liquid water persists. Oceans gather shallow at first, then deeper, covering much of the planet. In these early seas, minerals leach from the crust and complex chemical environments emerge along coasts in deep basins and around hydrothermal vents where hot water circulates through the young ocean floor. The exact timing of these transitions remains a matter of ongoing study. Ancient crystals of zircon found in some of the oldest surviving rocks carry isotopic signatures that suggest liquid water existed on Earth within a few 100 million years of its formation, at a time when the surface was still bombarded by frequent impacts from leftover debris. Other evidence points to a possible late heavy bombardment, a period during which the impact rate may have increased dramatically as giant planets rearranged their orbits and sent showers of comets and asteroids into the inner system. If such a surge occurred, it might have periodically sterilized the surface boiling oceans and melting crust, only for conditions to settle and cool again. In this picture, habitability would arise in fits and starts with windows of relative calm between catastrophic events. The geological record of these earliest times is fragmentary. Plate tectonics, the slow recycling of crustal plates driven by mantle convection, continually erases and renews the surface. Only a few tiny mineral grains and heavily altered rocks remain to speak for the first few 100 million years. From them and from comparisons with other planets and moons, scientists reconstruct a plausible scenario: a hot, active world with a dynamic interior, a global magnetic field shielding it from charged particles, oceans of liquid water, and an atmosphere rich in carbon dioxide and nitrogen, perhaps laced with methane, ammonia, and other reactive molecules. Under such conditions, complex chemistry becomes not only possible but inevitable. Energy flows from sunlight, from geothermal heat, and from chemical gradients at the boundaries between different materials. In the oceans and shallow pools, simple molecules collide and react, forming longer chains and more intricate structures. Clays and mineral surfaces may act as templates, concentrating certain molecules and encouraging specific reactions. Hydrothermal vents along mid-ocean ridges provide steady sources of heat and mineral-rich fluids, creating local environments where reduced and oxidized compounds meet driving chemical cycles that resemble in broad outline the energy pathways later used by living cells. Despite intense research, the exact path from non-living chemistry to the first self-replicating systems remains obscure. Several scenarios compete and perhaps overlap. Some models favor a world of self-copying RNA, like molecules that both store information and catalyze reactions. Others place metabolism first, with networks of chemical reactions gradually enclosing themselves within membranes to form primitive cells. Still others imagine that different components arise in different environments and later combine. What is clear is that once a system capable of imperfect replication appears, evolution through natural selection can begin exploring an immense space of variations. The earliest traces of life on Earth, preserved in ancient rocks as subtle chemical signatures or as microscopic structures that may be fossil microbes, seem to date back to at least 3.5 to 4 billion years ago, not long after the end of the most intense bombardment. This suggests that as soon as conditions allowed, life either arose or took hold. Whether this speed implies that life is common wherever similar conditions occur, or whether it reflects a rare fluke that happened quickly in this one case, is not yet known. Elsewhere in the solar system, worlds such as Mars, Europa, and Enceladus show evidence of past or present liquid water and possibly hydrothermal activity, hinting that the basic ingredients and energy sources for life are not unique to Earth. The emergence of a habitable planet thus appears as a natural extension of the processes that began with the formation of the solar system. Gravity shapes the disk collisions, build planets' internal heat, and differentiation generate magnetic fields and tectonics, and volatiles condense into oceans and atmospheres. The detailed balance among these factors determines whether a world remains barren or becomes a cradle for chemistry complex enough to cross the threshold into biology. On Earth, that threshold is crossed early in a setting shaped by both violence and stability, by impacts from space, and by the quiet cycling of water and rock. From this point forward, the story of the universe on this small world becomes inseparable from the story of life, even as the larger cosmos continues its own evolution beyond indifferent and immense. Once life gains a foothold on the young Earth, the planet's history begins to braid together with the slow evolution of the wider cosmos in a new way. Simple organisms, likely no more than microscopic cells, inhabit oceans that are still warm with geothermal heat and often tinted by dissolved minerals. They draw energy from chemical gradients, and in some lineages from the pale light of the early sun. Over vast stretches of time, these simple forms diversify. Some develop the ability to harness sunlight through photosynthesis, capturing photons and using their energy to build complex organic molecules from carbon dioxide and water. This cellular innovation has planetary consequences. As photosynthetic microbes spread through the oceans, they exhale oxygen as a waste product. At first, this oxygen reacts with dissolved iron and other reduced elements, rusting the sea floor and forming thick bands of iron-rich rock that will later be exposed on continents as layered monuments to ancient chemistry. Only after these sinks are saturated does oxygen begin to accumulate in the atmosphere. The Great Oxidation Event, as it will be called, transforms Earth's air from a reducing mixture into one where free oxygen becomes a significant component. For many existing organisms, this shift is toxic, driving extinctions and forcing adaptations. For others, oxygen opens new pathways, enabling more energetic metabolisms and more complex cellular structures. The planet's surface and sky respond as well. Ozone forms in the upper atmosphere, absorbing harmful ultraviolet radiation and shielding the surface. Weathering rates change as new minerals interact with the altered air, affecting the drawdown of carbon dioxide and feeding back on climate. The Earth begins to resemble more closely the world that later observers will know, though its continents are still shifting and its life remains entirely aquatic and microscopic. For long intervals, geological and biological change proceeds side by side at a pace that dwarfs human imagination. Continents merge into supercontinents and break apart again as tectonic plates drift on the convecting mantle. Glaciations advance and retreat, sometimes covering large portions of the globe in ice. During one extreme episode, ice sheets may reach close to the equator, prompting the idea of a snowball Earth where most surface water freezes. Volcanic outgassing gradually builds up greenhouse gases, warming the planet and eventually melting the ice. Each such cycle places stress on the biosphere, pruning some branches while allowing others to flourish. At cellular and molecular scales, evolution continues its patient experimentation. Organisms develop internal compartments, cytoskeletons, and more elaborate genetic regulation. Some cells engulf others without digesting them, forming symbiotic partnerships. In this way, ancestors of mitochondria and chloroplasts take up residence inside larger host cells, giving rise to eukaryote cells with nuclei and complex internal architecture. This step, like the emergence of photosynthesis, changes the possible range of life's forms. Multicellularity appears as some organisms begin to adhere, coordinate, and specialize. Simple colonies give way to bodies, where different cells perform different roles. Initially, these experiments remain soft-bodied and seldom leave clear fossils, but over time, the variety and size of multicellular organisms increase. In the oceans of the late Precambrian era, frond-like and quilted forms populate the seafloor, hinting at a rich ecology that will soon shift into an even more diverse mode. Then in what will be called the Cambrian explosion, the fossil record shows a relatively rapid appearance of many animal body plans. Hard parts such as shells and exoskeletons become common, improving preservation and making the diversity visible in rock. Eyes, jaws, limbs, and other anatomical innovations allow predation, burrowing, and swimming in new ways. Food webs grow more intricate and evolutionary pressures accelerate. Although this apparent suddenness is partly a matter of incomplete preservation, the underlying reality is still one of accelerated diversification. Over the following hundreds of millions of years, life moves on to land. Plants colonize damp shorelines, then spread inland as roots and vascular tissues evolve. Fungi and arthropods accompany them, breaking down organic matter and building soils. Vertebrates first confined to water extend their reach with lungs and limbs. Amphibians venture onto land, followed by reptiles and eventually the first mammals and birds. Forests rise and fall, covering continents in green and then receding during climatic shifts and mass extinctions. Throughout this long narrative, the wider cosmos continues its own evolution. The Milky Way orbits slowly within the local group of galaxies. Star formation rates wax and wane, supernovae explode in distant arms, and comet reservoirs at the fringes of the solar system are periodically perturbed by passing stars or by subtle gravitational resonances. Occasionally, a fragment of ice or rock from these distant realms falls toward the inner system and intersects Earth's orbit. Most burn up harmlessly in the atmosphere, but a few large impacts leave craters and sometimes trigger global changes. One such event at the close of the Cretaceous period contributes to the extinction of the non-avian dinosaurs and many other species, clearing ecological niches that mammals will later fill. This intertwining of celestial dynamics and planetary biology underscores that Earth's story is never isolated. The quiet stability that allows complex life to evolve is itself the product of larger structures and motions. The sun's relatively steady output, the protection offered by Earth's magnetic field and atmosphere, the gentle character of the planet's orbit and axial tilt, and the moderating influence of its large moon all owe their existence to prior cosmic events, the chemical enrichment of the interstellar medium by ancient stars, the specific conditions of the solar nebula, the giant impact that created the moon, and the migration history of the outer planets. Within this context, the emergence of self-aware observers is a recent and delicate development. Only in the last few tens of thousands of years do hominins begin to express symbolic thought in art, language, and technology. Human societies grow, spread, and transform the surface of the planet on timescales that are instant compared with the eons that preceded them. At some point in this rapid flowering, members of one species look up at the night sky and begin to ask where it all comes from. The sense of wonder that drives these questions is itself a product of the long chain of cosmic and biological evolution atoms forged in ancient stars, assembled into brains capable of reflecting on their own origin. When humans eventually design instruments sensitive to radio waves and X-rays to microwaves and infrared light, they extend their senses far beyond the surface of their small world. The cosmic microwave background, the distribution of galaxies, the spectra of distant supernovae, and the orbital motions of planets all become data points in a growing attempt to reconstruct the history of the universe. In this way, the narrative loops back on itself. The universe evolves to a state in which tiny parts of it can observe and model the whole. The same physical laws that govern the first expansion, the cooling plasma, the formation of stars and galaxies, and the assembly of planetary systems also shape the neurons that flicker in the human brain. The questions those neurons pose about beginnings, endings, and the nature of nothingness are not external to the story, but arise from within it as natural a consequence of cosmic evolution as any cluster of galaxies or star-forming nebula. As human understanding of the cosmos deepens, attention returns again and again to the question of how space and time themselves behave when pushed to their limits. The theory of general relativity proposed in the early 20th century describes gravity not as a force pulling on objects from a distance, but as the curvature of space and time caused by mass and energy. In this picture, planets move along paths that follow the contours of a four-dimensional fabric, bending gently around stars and more sharply around dense bodies like neutron stars and black holes. Light itself travels along these curves so that beams from distant galaxies are deflected when they pass near massive clusters, producing arcs and multiple images that observatories record as gravitational lenses. On everyday scales, this geometric view of gravity reduces to the familiar pull that holds feet to the ground and keeps planets in their orbits. On cosmic scales, it explains how the universe can expand as a whole, with space stretching between galaxies even as local systems remain bound. Yet the same equations that describe these graceful motions also predict their own breakdown under extreme conditions. When enough mass is compressed into a small enough region, the curvature of space and time becomes so intense that nothing, not even light, can escape. A black hole forms surrounded by an event horizon beyond which events cannot influence the outside world. Inside such an object, the theory indicates that matter collapses toward a central singularity, a point where density and curvature diverge, and the equations cease to provide meaningful answers. A similar singularity appears when the equations are applied not to a collapsing star, but to the universe as a whole traced backward in time. If one assumes a simple homogeneous cosmos and follows its expansion in reverse, the scale factor that measures distances between points shrinks steadily until it reaches zero at a finite time in the past. At that instant, according to the classical equations, densities and temperatures become infinite and space and time themselves are squeezed into a point with no extension. This is the mathematical Big Bang, a singular boundary where the familiar fabric of reality tears. Physicists generally interpret such singularities not as literal features of nature, but as signs that a theory has reached the edge of its domain of validity. In everyday situations, air behaves as a continuous fluid, and equations that treat it as such give accurate predictions. At microscopic scales, however, the discrete nature of molecules matters, and the continuum description fails. Something similar is expected to happen with space and time near the Big Bang and inside black holes. The smooth geometry of general relativity, so successful at larger scales, must give way to a more fundamental description in which quantum effects are no longer negligible. Quantum theory reveals that matter and energy have a dual character, behaving sometimes like particles and sometimes like waves, and that certain quantities can never be specified with arbitrary precision. When fields are quantized, their lowest energy state is not a featureless zero, but a restless vacuum filled with temporary fluctuations. On laboratory scales, this quantum behavior produces phenomena such as the quantization of atomic spectra and the tunnel effect, where particles pass through barriers that classical physics says should be impenetrable. At cosmic scales, it implies that no field, including the gravitational field that shapes space and time, can remain perfectly smooth. To combine general relativity with quantum principles is to ask how the very fabric of space and time behaves when it becomes subject to uncertainty, superposition, and fluctuation. Attempts to build such a theory of quantum gravity have taken several paths. One approach treats space itself as composed of discrete units connected in a network with areas and volumes that come in smallest possible increments. Another imagines that the basic entities are not particles but tiny strings, whose vibrational modes give rise to the known particles and forces. In both cases, the goal is to replace the singular point of the classical Big Bang with a more benign structure, perhaps a bounce, a transition, or a region where the notion of time loses its usual meaning. These models suggest that when densities approach the Planck scale, a regime defined by combinations of fundamental constants, quantum effects, can resist further compression, much as the quantum pressure of electrons supports white dwarfs, and the quantum pressure of neutrons supports neutron stars. Instead of collapsing into an infinite density, the universe could reach a maximum curvature and then rebound, turning contraction into expansion. In some scenarios, our current expanding universe might thus be only one phase in a longer sequence of cycles. In others, the Big Bang becomes a boundary between two qualitatively different regimes, one of which cannot be described by any classical notion of space and time at all. Observational evidence for or against such ideas is difficult to obtain. The light that telescopes collect comes only from epochs long after the earliest instants, and the gravitational waves currently detectable also sample relatively late events such as merging black holes. Any signature of quantum gravity from the very beginning would have to survive through inflation recombination and the entire subsequent history of the cosmos, encoded perhaps as a subtle pattern in the distribution of galaxies or in the polarization of the ancient microwave background. Researchers have proposed specific imprints to look for, such as slight deviations from the simplest spectrum of primordial fluctuations or particular correlations at large angular scales, but so far no clear, unambiguous trace has emerged. Still, the very success of general relativity in every tested regime makes the existence of a deeper layer almost certain. A theory that unifies the geometric view of gravity with the probabilistic world of quantum mechanics would not only resolve the mathematical singularities but also clarify what it means to speak of a beginning of time. It might reveal that time is emergent, arising from more fundamental timeless relations, or that before the Big Bang there existed some other kind of process that cannot be described in terms of earlier and later. Until such a framework is found and confirmed, the origin remains framed by two complementary descriptions that each fail in the place where the other should take over: general relativity, leading confidently back to a singularity it cannot handle, and quantum theory insisting that fluctuations and discreteness must intervene before that point is reached, without yet specifying exactly how they do so. Between these partial views lies a gap that is both a challenge and an invitation, a region of conceptual space, where new ideas about the nature of reality may one day emerge, altering not only the scientific account of the beginning, but also the intuitive sense of what it means for there to have been a time when there was no time at all. Among the attempts to replace the singular beginning of classical cosmology, one of the most evocative is the idea that the universe may not have a unique birth at all, but instead passes through cycles of contraction and expansion. In such scenarios, the Big Bang is not an absolute origin, but a transition, a bounce, where a previous phase of the cosmos gives way to the one now observed. The notion of a cyclic universe has deep historical roots, yet in contemporary physics it arises from efforts to combine general relativity with quantum effects and with the strange behavior of dark energy. In a simple picture, a universe that expands under its own momentum might eventually slow, halt, and reverse if gravity from matter and radiation is strong enough. Expansion would give way to contraction, galaxies would draw closer together, temperatures would rise, and over immense timescales the cosmos would collapse toward a dense final state. If quantum gravity intervenes before a singularity forms, the collapse could rebound, initiating a new expansion, The bounce would stand in place of the classical singular point with the arrow of time continuing smoothly through it for any hypothetical observer carried along by the cosmic flow. In this view, the present universe would be only the latest in a chain of eons, each one preceded by another and followed by the next. Some models envision that almost all memory of previous cycles is erased in each bounce with matter and radiation thermalized into a nearly uniform state. Others allow for traces to survive encoded in the pattern of primordial fluctuations, or in the properties of dark matter and dark energy that carry information across cycles. One limiting factor in such scenarios is entropy, a measure of disorder. In a closed universe that repeatedly expands and contracts, entropy tends to increase from cycle to cycle, suggesting that later cycles should be larger and longer than earlier ones. This raises questions about whether the chain of cycles can extend infinitely into the past, or whether there must be some earliest phase even in a cyclic model. Some versions address this by allowing the overall scale of the universe to grow from cycle to cycle so that entropy density can reset even as total entropy rises. Within these broad ideas, more specific proposals take shape. In loop quantum cosmology, a simplified application of loop quantum gravity, the equations suggest that the quantum geometry of space becomes effectively repulsive at very high densities, preventing the scale factor from reaching zero. Instead of a singular Big Bang, the model yields a bounce where a contracting branch transitions into an expanding one. Whether any imprint of that pre-bounce world could survive in a detectable way is an open question. Other approaches, such as ekpyrotic models inspired by string theory, imagine that what appears as a Big Bang is the result of a collision between higher dimensional branes that move in a larger space. In those pictures, each cycle involves a slow contraction that smooths and flattens the universe, followed by a bounce generated by brain interactions, after which ordinary expansion resumes. Under some conditions, the smoothing phase can produce the kind of nearly scale invariant spectrum of primordial fluctuations that observations of the cosmic microwave background demand, offering an alternative to inflation. These constructions are mathematically rich but depend on ingredients far beyond current empirical reach. The idea of a cyclic cosmos also interacts with the concept of dark energy. Observations indicate that the expansion of the universe is currently accelerating, driven by a component whose pressure is negative. If this dark energy behaves like a cosmological constant remaining the same in time, then the expansion will continue to speed up, indefinitely diluting matter and radiation and pulling galaxies beyond each other's horizons. In such a scenario, a future contraction seems unlikely. However, if dark energy evolves, perhaps decaying or changing sign over extremely long timescales, it could eventually allow gravity to regain dominance and start a new phase of collapse. Conversely, some models explore the possibility of a phantom-like dark energy whose density increases with time, leading not to a future contraction, but to a big rip, a divergence in which the scale factor and expansion rate blow up and bound structures are torn apart. Each of these extreme fates poses its own version of the singularity problem and invites speculation about what, if anything, might follow. In thinking about cycles, bounces, and rips, a pattern emerges. Whenever the classical equations predict infinite quantities, theorists look for mechanisms by which new physics can intervene. The form that this intervention takes is guided partly by mathematical consistency and partly by the desire to preserve some form of continuity to avoid an absolute beginning or end. A cyclic universe fits this desire naturally, replacing a unique origin with an endless rhythm. Yet even if such a rhythm exists, it raises its own questions. Why does anything cycle at all rather than nothing existing? What sets the rules that govern the transitions between phases? A cyclic model shifts the focus of mystery without eliminating it, turning the sharp question of a single beginning into the broader puzzle of an eternal process whose underlying cause remains unknown. In the quiet hours when these ideas are considered, the cosmic story seems to widen rather than resolve, revealing not a single narrative arc, but a possible tapestry of repeated expansions and contractions, each leaving only faint hints in the observable sky. In some lines of thought about the origin of the universe, the idea of cycles takes on a more subtle form than simple bounces of expansion and contraction. One such proposal imagines that what begins and ends is not space itself, but the scale at which its geometry is measured. In this picture advanced by certain interpretations of conformal cyclic cosmology, each long era of cosmic history, each eon stretches so far into the future that all structures with mass gradually dissolve. Stars burn out, leaving white dwarfs, neutron stars, and black holes. Over unimaginable timescales, even these remnants change. Black holes slowly evaporate through the emission of quantum radiation, losing mass bit by bit until they vanish. Particles with mass may decay into radiation as well. The universe that remains becomes an ever more dilute bath of massless particles, primarily photons, streaming through an expanding, cooling space. In such a state, the usual notion of scale begins to lose meaning. Without massive objects to act as rulers and clocks, no natural length or time interval stands out. Only the angles between trajectories, the conformal structure of space and time, retain physical significance. In this limit, according to the idea, the distant future of one eon can be mathematically reshaped so that it resembles the very beginning of another. The infinitely stretched endpoint and the sharply curved starting point become, under a conformal transformation, two faces of the same underlying structure. From this point of view, the Big Bang is not an absolute boundary, but a bridge between successive eons, each of which passes through its own long history before fading into a scale-free state that seeds the next. The appeal of such a model lies in its ability to connect the extreme past and future without introducing a singularity in the usual sense. Instead of densities blowing up to infinity, the problematic regime is replaced by a transition in which the distinction between large and small dissolves. Time within each eon still has a clear direction. Entropy increases, structures form and decay, and observers, if they exist, experience an arrow of time from past to future. Yet the chain of aeons as a whole has no beginning in the familiar sense. It extends indefinitely in both directions, each link bounded by conformal bridges where the language of ordinary clocks and rulers no longer applies. To move from mathematics to possible observation, proponents of such ideas look for faint traces that one eon might leave in the next. If powerful events occur near the end of an aeon, such as collisions of supermassive black holes, the energy they release in gravitational waves could in principle imprint patterns on the primordial radiation of the following aeon. When translated through the conformal mapping, these disturbances might appear as subtle circular features or anomalies in the temperature of the cosmic microwave background. Searches in satellite data have claimed hints of such patterns rings where the variance in temperature is slightly lower than expected from random fluctuations alone. These claims are controversial. Other analyses argue that the same features can arise by chance in a universe governed by the standard inflationary model, and that no statistically significant evidence for imprints of previous eons has yet been found. The debate highlights the difficulty of extracting robust signals from a single observable sky where every pattern must be weighed against the possibility of coincidence. Even without decisive observational support, the concept of conformal cycles serves as a thought experiment that stretches intuition about time. It suggests that the deep question may not be why there is something rather than nothing, but why the universe has the particular large-scale structure and history that it does. In an eternal chain of eons, each with its own patterns of galaxies, stars, and possibly life, the conditions of any given aeon might reflect both universal laws and specific features inherited through the conformal boundary. Whether or not this is how reality behaves, exploring such possibilities sharpens the sense that the Big Bang as seen from within one eon might be only a partial view of a larger, more intricate story. At the same time, the speculative nature of these models acts as a reminder of the limits of current knowledge. The equations that allow the conformal mapping are elegant, but they rely on assumptions about the ultimate fate of matter and the exact behavior of fields at extremely low energies regimes far beyond present experimental reach. Unknown processes could intervene, altering the thermodynamic end state or introducing new kinds of structure that break the simple picture of a massless, scale-free future, until more data arrive either from more precise measurements of the cosmic microwave background or from other probes of fundamental physics. Conformal cyclic cosmology remains one of several competing attempts to extend the narrative beyond the visible beginning. It takes the familiar storyline of expansion from a hot, dense state and embeds it within a repeating tapestry, trading a single origin for an endless succession of eras, each separated from the next by a boundary that looks from the inside like the moment when time and space first come into being. In quiet reflection, this framework allows the mind to picture a universe that never truly starts or ends, but continually renews its capacity for structure and story. Galaxies, planets, and living beings then appear as temporary patterns in an ongoing flow, arising, flourishing, and fading within one eon before the great thinning resets the stage. The notion does not answer why the flow exists at all, but it offers a calm image of continuity where a sharp edge might otherwise seem to stand. Alongside cyclic visions of the cosmos, another family of ideas suggests that the universe observed from Earth is only one region in a far larger structure, a single bubble in an endless multiverse. In this view, the apparent beginning marked by the Big Bang is not the creation of all that exists, but the local onset of a hot, dense phase inside a pre-existing and still evolving background. The most common route to such a picture arises from inflationary theory. If the same physics that drove the early rapid expansion remains active in some regions while shutting off in others, then inflation does not end everywhere at once. Instead, patches where the inflationary field decays give birth to pocket universes filled with hot plasma that then follow their own Big Bang like histories, while inflation continues elsewhere, constantly generating new pockets. The result is a fractal-like arrangement of inflating and non-inflating domains, an eternally self-renewing multiverse. Within each pocket, physical conditions can differ. The values of fundamental constants, the relative strengths of forces, and even the number of familiar spatial dimensions may be set by the way the underlying fields settle into one or another of many possible energy minima, often called a landscape. Some minima may allow long-lived, stable universes with stars, galaxies, and perhaps life. Others might produce universes that expand too fast for structures to form, or that collapse again almost immediately, or that lack rich chemistry. In such a setting, observers naturally find themselves in a pocket where conditions permit their existence, not because those conditions are preferred by any deeper principle, but because other pockets remain forever unobserved and uninhabited. This line of reasoning introduces a kind of selection effect into cosmology. The values of certain parameters, such as the density of dark energy, appear in current measurements to be small but not zero, delicately balanced between enabling cosmic acceleration and allowing large-scale structure to develop. In the multiverse picture, this balance is not mysterious. Pockets where dark energy is much larger never grow galaxies and so never host observers who could measure it. Pockets where it is much smaller may be rare or unstable. The observed value then reflects what is typical among the subset of universes that can support complex structures, even if it is unusual across the full landscape. For some, this anthropic flavor feels uncomfortable, replacing predictive calculation with statistical arguments about unobservable regions. For others, it represents a natural extension of the Copernican lesson that Earth is not central and that human perspectives are not privileged. Just as the planet is one world among many and the galaxy one among countless others, so the visible universe may be only one patch in an enormous and perhaps infinite mosaic. The challenge lies in formulating this picture in a way that makes contact with observation. Direct detection of other pocket universes seems unlikely, as they are by construction separated from the local region by inflating space that expands faster than any signal can cross. Yet certain processes could in principle leave subtle marks. If two pockets nucleated close together and their expanding boundaries collided, the interaction might produce a distinctive pattern in the distribution of temperatures or polarizations in the cosmic microwave background, perhaps a circular feature or a localized distortion. Searches for such signatures have been carried out using satellite data, yielding at best tentative hints and generally no convincing evidence. Another route involves statistical predictions. If the multiverse generates a huge ensemble of universes with varying parameters, then the distribution of those parameters among the subset compatible with observers might be calculable. One could then ask whether the values measured in the local universe are typical within that conditional distribution. Some attempts along these lines have shown promising agreement for dark energy, but they depend sensitively on assumptions about how to measure typicality in an infinite or very large ensemble, an issue known as the measure problem. Without a well-defined measure, probabilities become ambiguous, and comparisons between theory and observation lose their footing. The multiverse idea also raises conceptual questions about what it means to explain a phenomenon. In a traditional model with a single universe, one expects to derive the properties of that universe from a small set of fundamental principles. In a multiverse, some properties might be environmental, varying from region to region, while the underlying laws dictate only the space of possibilities. Explaining why a parameter has its observed value then becomes a matter of showing that this value lies within the range that allows observers, and that it is not improbably rare within that range. Whether such an explanation is satisfying depends partly on philosophical taste. Independently of these debates, the mathematical structures that give rise to multiverse-like behavior arise naturally in several attempts at unifying physics. Inflationary potentials with many metastable vacuous string theory landscapes with an enormous number of compactification modes and quantum cosmological models that treat the wave function of the universe as branching into many classical histories All point toward a reality that may be more richly partitioned than the naive picture of a single unique cosmos. Even if only one branch corresponds to the actual experience of any given observer, the full framework may require the existence of many branches to maintain coherence and unitarity. From the vantage point of a small planet orbiting an ordinary star, these possibilities are difficult to assess. Telescopes reveal only one observable universe, with one set of constants and one history. The evidence extracted from light and particles must be stretched to infer the nature of regions forever hidden beyond the cosmic horizon. In this sense, the multiverse remains more a proposal about what might lie beyond the boundary of observation than a theory in the usual empirical sense. Yet the very act of contemplating such structures changes the way the beginning is imagined. Instead of a single moment when everything appears at once, there may be a continual process in which new regions with Big Bang-like beginnings bud off from an inflating background or from higher dimensional interactions. The question what happened before the Big Bang then shifts again from seeking a prior time to considering the larger system within which the local Big Bang is one event among many. In this broader frame, the nothing from which the local universe seems to arise may itself be a kind of something, a persistent process or field whose fluctuations constantly generate new domains. The emptiness that precedes a particular beginning becomes not an absolute void, but an active medium restless with potential structure, of which the visible universe is only one realization among countless others. As theories of the early universe and of the multiverse grow more intricate, attention turns to the underlying stage on which all such scenarios play out: the vacuum itself. In everyday language, a vacuum is the absence of matter, an empty volume from which air and dust have been removed. In modern physics, the concept is more subtle. The vacuum is not merely a region where particles happen to be missing, but the lowest energy state of quantum fields that pervade all of space. These fields cannot be completely still. Even in their ground state, they exhibit fluctuations, brief excitations that rise and fall in accordance with the uncertainty principle. Particle and antiparticle pairs flicker into existence and annihilate virtual processes that do not persist long enough to be directly observed, but nonetheless leave measurable effects. Experiments sensitive to these fluctuations detect forces between conducting plates placed very close together in a vacuum, a phenomenon known as the Casimir effect. The plates alter the allowed modes of the electromagnetic field between them, changing the vacuum energy in that region compared with the surrounding space, and producing a tiny but real pressure that nudges the plates toward each other. Such observations confirm that what seems like empty space is at a deeper level an active medium filled with potential. In curved space-time, the structure of the vacuum becomes even richer. Different observers moving along different trajectories can disagree about what constitutes the vacuum. An accelerating detector in otherwise empty space can register a bath of particles, an effect related to the Unruh phenomenon, while an observer at rest sees none. Near the event horizon of a black hole, quantum fluctuations give rise to Hawking radiation, as pairs of virtual particles are separated by the strong gravitational field, allowing one to escape to infinity while the other falls in. The black hole slowly loses mass through this process, converting what was once a purely geometrical object in classical general relativity into a quantum system with temperature and entropy. These examples show that the vacuum is not a fixed, featureless backdrop. It responds to geometry, acceleration, and boundary conditions, and in turn influences the behavior of matter and space-time. In cosmology, the vacuum appears again in the guise of dark energy. Observations of distant supernovae and of the large-scale distribution of galaxies indicate that the expansion of the universe is accelerating as if driven by a uniform energy density that does not dilute as space grows. One natural candidate for this is vacuum energy, the net effect of all quantum fluctuations of all fields. When the energy of the vacuum is inserted into Einstein's equations, it plays the role of a cosmological constant exerting a negative pressure that pushes space to expand faster. However, attempts to calculate the vacuum energy from quantum field theory lead to an enormous discrepancy. Naive estimates produce values many orders of magnitude larger than those inferred from cosmological data. This mismatch between theory and observation is sometimes described as one of the worst agreements in physics. It suggests that something is profoundly misunderstood either about the way vacuum energy gravitates or about the structure of quantum fields at very high energies. Various mechanisms have been proposed to cancel or reduce the vacuum contribution, but none has yet achieved wide acceptance. The small but non-zero value of dark energy remains a persistent enigma. In some multiverse scenarios, the problem is softened by environmental selection. If different regions of the larger reality realize different vacuum energies, then only those with values in the narrow range that permit galaxies and long-lived stars can host observers. The observed smallness of dark energy then becomes a selection effect. Yet this does not explain why the possible values cluster around zero rather than some other scale, nor why the actual value appears comparable to the matter density at the present epoch, a coincidence often called the cosmic coincidence problem. The vacuum thus occupies a central, ambiguous role in the story of the universe. It is the medium from which particles and structures emerge, the reservoir that may drive cosmic acceleration, and the arena in which quantum gravity must eventually be defined. At the same time, it invites the deepest questions about the nature of nothing. If the vacuum is seething with fluctuations, if it has energy and structure and can give rise to particles when disturbed, can it reasonably be called nothing at all? Some physicists argue that what is often described as creation from nothing in cosmological models is better understood as a transition from one state of the vacuum to another, or from a quantum gravitational regime without classical spacetime to one in which such spacetime emerges. In these views, the apparent origin of the universe is a change within an underlying system that already exists, even if that system does not resemble space-time and matter in any familiar form. Others maintain that physical theories by construction describe relations among states within some framework and cannot meaningfully address why that framework exists at all. They can show how a universe like the observed one can arise from quantum fluctuations in a vacuum or from tunneling between configurations in a larger space of possibilities, but they remain silent about why there is a vacuum or a space of possibilities in the first place. The word nothing for them refers only to the absence of excitations within a given model, not to an absolute non-being. Between these positions lies a spectrum of interpretations. Some see in the active vacuum a hint that reality is fundamentally process rather than substance, a continuous transformation in which what appears as emptiness at one scale or description is full of structure at another. The early universe in this light emerges not from a void that is truly blank, but from a quantum state with no classical space or time, whose internal dynamics give rise to an expanding cosmos with particles, fields, and observers. The Big Bang then becomes a phase change rather than a creation ex nihilo, a shift in the pattern of the vacuum. From the limited vantage of one region and one epoch, such distinctions may blur. Measurements register only the consequences of the vacuum's presence, the acceleration of the expansion, the behavior of fields near boundaries, the faint radiation from black holes, and perhaps in the most delicate observations, subtle imprints from the earliest instants of cosmic evolution. The deeper question of whether the vacuum is something or nothing, and of what it means for anything at all to exist, remains suspended between physics and philosophy, an open space where equations stabilize predictions, while leaving untouched the quiet astonishment that there is a stage on which any story can unfold. As inquiry reaches deeper into the question of beginnings, attention returns to the nature of time itself, for any story about a first moment assumes that time already behaves like a line along which events can be placed. General relativity treats time as one dimension of a four-dimensional continuum woven together with the three spatial dimensions into a single fabric. In many solutions of Einstein's equations, this fabric can be drawn as a block in which all events, past, present, and future, coexist in a fixed geometric relationship. The flow of time that conscious beings experience then appears not as a change in the block itself, but as a feature of how observers trace their own world lines through it, assembling slices of the whole into a sequence. This block universe picture clashes with everyday intuition, which insists on a moving present, on a clear separation between what has happened and what is yet to come. Yet even in ordinary physics, the fundamental laws that govern particles and fields are largely time-symmetric. They do not distinguish between forward and backward, treating both directions equally valid when written in equations. The one obvious exception is the growth of entropy, the tendency of systems to evolve from ordered states into more disordered ones. This statistical behavior produces the familiar arrow of time, broken cups do not reassemble, cream poured into coffee does not spontaneously separate, and stars exhaust their fuel rather than refilling themselves from cooled ashes. In cosmology, the arrow of time is tied to the universe's low entropy beginning. A hot, dense plasma might seem highly disordered, yet in gravitational terms, the early universe is extremely special. Matter is spread almost uniformly with only tiny fluctuations, rather than clumped into black holes and dense structures that would represent a much higher entropy configuration. As space expands, gravity amplifies the small irregularities and structure forms. Entropy increases as galaxies, stars, and eventually black holes appear. The puzzle then becomes why the universe started in such an unlikely low entropy state. Some cyclic and multiverse models attempt to address this by suggesting that a smoothing phase precedes each expansion, or that we inhabit a region selected from a much larger ensemble where low entropy patches sometimes arise by chance. Others posit that a deeper law sets the boundary conditions of the universe in a way that enforces low initial gravitational entropy. None of these proposals is universally accepted, and the origin of the arrow remains one of the most persistent mysteries in fundamental physics. Quantum mechanics complicates the picture further. At the microscopic level, the evolution of a closed system is described by a wave function that changes in a way that preserves information and is in principle reversible. Yet measurements in the laboratory appear to produce definite outcomes with probabilities given by the squared amplitudes of the wave function. Before measurement, a system can exist in a superposition of possibilities after it seems to occupy only one. This apparent collapse breaks time symmetry and introduces an effective arrow. Different interpretations of quantum mechanics handle this transition in different ways. Some treat collapse as a real physical process that adds a stochastic time-directed element to the otherwise symmetric equations. Others argue that all possible outcomes continue to exist in separate branches, and that what is experienced as collapse is merely a shift in the observer's place within an ever-branching multiverse. Still others emphasize decoherence, the spreading of quantum correlations into the environment, which makes certain outcomes effectively classical and irreversible from the perspective of local observers. When these ideas are applied to the entire universe, the usual distinction between system and observer breaks down. In quantum cosmology, there is no external measuring device. The universe must be described as a whole. One influential equation in this context, sometimes called the Wheeler-DeWitt equation, resembles a stationary wave equation without an explicit time variable. It suggests that at the most fundamental level, the quantum state of the universe may be timeless. Time in this view emerges only when that state is examined in terms of correlations between different parts. Subsystems can then serve as clocks for each other, and an effective temporal order appears. This relational time does not exist as an independent background, but as a pattern within the correlations of the global state. Under such a framework, the Big Bang is not a moment when time begins in an absolute sense, but a region in the space of possible correlations where the effective notion of time first becomes meaningful. Before that, the concept of earlier and later may simply not apply. Instead, there exists a timeless quantum structure whose internal relations allow in some regimes the appearance of a classical space-time with a familiar arrow. To minds evolved within that emergent time, the idea of a timeless underlying reality feels elusive. Language built around sequences and causes struggles to grasp a domain where sequence is not fundamental. Some approaches attempt to bridge the gap with path integrals over geometries, summing over all possible histories the universe might have had, weighted by their action. In such path integral cosmology, the universe is not compelled to follow a single classical history. Rather, classical space-time emerges as an approximation where many possible histories interfere constructively to produce a dominant pattern. The beginning, then, is not a single point, but a region in this space of histories where quantum behavior is particularly strong. Whether time and space emerge from something yet more abstract, perhaps a network of quantum entanglement or an algebraic structure without classical interpretation, remains an open question. Ideas from holography hint that space-time geometry may be encoded in patterns of entanglement in a lower dimensional theory, suggesting that the familiar picture of a smooth continuum is secondary to more primitive informational relationships. If so, asking what happened before the Big Bang might be akin to asking what lies north of the North Pole, not only because of the geometry of time, but because beyond a certain domain the notion of temporal location loses all grounding. In the quiet gap between what is known and what is proposed, a picture slowly coalesces in which the origin of the universe, the arrow of time, and the emergence of space-time itself are intertwined. The low entropy beginning that sets the direction of time, the apparent singularity where classical equations fail, and the quantum description that hints at timelessness all point toward a layer of reality where the categories of before and after something and nothing may need to be redefined. From the vantage of the present where clocks tick and galaxies recede, that layer remains largely hidden, glimpsed only through the constraints it imposes on observable structures and through the mathematical coherence of theories that reach toward it. In the long arc from the first flicker of expansion to the present moment of reflection, the question that began this exploration still waits at the edge of thought. How can there be a before if time itself is part of what begins? How can a universe emerge from what is called nothing when every attempt to describe that nothing reveals structure, potential, or law? Modern cosmology offers layered answers, none complete, each illuminating a different aspect of the mystery. The classical picture of a hot Big Bang presents a universe that expands from a state of extreme density, but leaves the singular starting point blank, a marker where the equations no longer speak. Inflationary models smooth the early universe and explain the pattern of fluctuations that later grow into galaxies, yet they replace a sudden beginning with an episode of rapid expansion whose own origin is not specified. Cyclic and conformal scenarios extend history beyond the apparent start, trading a unique birth for a chain of eras, while multiverse constructions embed the local Big Bang in a wider landscape of possible regions. Quantum gravity approaches hint that the very concepts of space, time, and vacuum may be emergent rather than fundamental, suggesting that what is experienced as a beginning is a phase transition in a deeper structure that does not itself unfold in time. In all of these frameworks, the word nothing gradually loses its ordinary meaning. What appears as empty space is already filled with quantum fields, their fluctuations giving rise to forces, particles, and perhaps to dark energy. A vacuum in this sense is not an absence of everything, but a specific state of something with properties that can be measured and altered. Creation from such a vacuum is not creation from absolute non-existence, but a reshaping of an underlying medium. Even in models where the universe tunnels into being from a prior state, the tunneling occurs within a mathematical structure that presupposes rules and relations. The nothing in which the universe is said to originate is therefore not a simple void, but a domain that theory regards as real enough to support dynamics. At a more abstract level, attempts to describe a quantum state of the universe without time suggest that the usual distinction between before and after may be a feature of emergent descriptions rather than a fundamental trait of reality. In such views, there is no answer to what happened before the Big Bang because the terms of the question rely on an ordering that does not exist in the underlying theory. Instead, there is a structure from which sequences arise only in certain regimes. Time may emerge from correlations in a deeper, timeless state, as temperature emerges from the collective motions of many particles. The Big Bang then marks the boundary where a time-based description becomes valid, not a moment when a pre-existing clock suddenly starts. For minds that live within time endings and beginnings are natural anchors. Each life has a start and a finish. It is almost irresistible to project the same pattern onto the universe as a whole, to imagine a first instant when everything begins and to ask what was there before. Yet the picture assembled from observation and theory points toward a reality in which the notion of a global beginning may be more like a useful approximation than an ultimate fact. The earliest moments that can be reconstructed with confidence already presuppose a working framework of laws and quantities. Pushing the description back further reveals not a featureless emptiness, but a region where current concepts fail and where new principles must operate. Whether those principles involve discrete quanta of space and time, networks of entanglement, higher dimensional structures, or something still unimagined, they will likely require abandoning some of the intuitions that make the idea of nothing so compelling. As understanding deepens, the stark contrast between something and nothing softens. The vacuum turns out to be animated by fluctuations. Singularities are replaced in many proposals by bounces, transitions, or boundaries in a larger configuration. What remains is the presence of regularities that can be expressed as laws, patterns stable enough for stars and planets to form and for living beings to arise who can notice them. The deepest puzzle may therefore not be how something emerges from nothing, but why there is an ordered structure at all rather than chaos. Physics traces patterns within what is given and explores their consequences, but it does not reach beyond the assumption that some form of reality exists. The leap from absolute nothing to such a reality may be beyond the scope of experiment, yet the attempt to approach that boundary shapes the entire enterprise. By pushing theories back toward the earliest moments, by examining the vacuum and the arrow of time, cosmology brings the question of nothingness into sharper focus, even as it acknowledges that a final answer may remain out of reach. The story that emerges is not one of a simple beginning and a simple void, but of an evolving structure whose origins recede as understanding grows. The universe appears as a continuous unfolding of patterns rooted in a foundation that need not itself be temporal. The phrase "before the Big Bang" becomes a pointer toward this foundation, a way of naming the region where current concepts fade. There at the edge of explanation, the idea of nothing merges with the sense of an unknown that is not empty but simply not yet described, an open space in which future insights may one day draw new lines between what is meant by beginning by time and by the quiet word nothing.